Okay, another problem. The heat flux that is applied to one face of a plane wall is Q second equals to 20 watt per meter square. The opposite face is exposed to air at a temperature of 30 degrees with a convection heat transfer coefficient of 20 watt per meter square Kelvin. The surface temperature of the wall exposed to air is measured and found to be 50 degrees. Do steady state conditions exist? If not, is the temperature of the wall increasing or decreasing with time? Okay, so here also it's a simple problem just to keep in mind how to apply the energy balance. So if we consider the wall, always do a small scheme that can help you to see the different processes involved. So you have your wall, okay? They are telling you that from one face side, we are imposing a flux of 20 watt per meter square. So we have a flux that energy that is coming in at a rate of 20 watt per meter square, while the opposite face is exposed to air. So here we have a fluid, air. The temperature of air is 30 degrees. And because in general, whenever we have contact between a fluid and a surface, we have heat transfer by convection. And they gave us the heat transfer coefficient by convection H equals to 20 watt per meter square Kelvin. Now, they told us that from measurements, the temperature of the outer surface of the wall was measured to be 50 degrees. Now, the question is to know if we have transient variation of temperature within the wall. So we want to know if the temperature is increasing, decreasing with time, or if we have steady state profile of temperature. If you have such a question, what is the best thing to do first?
Energy balance.
Exactly. We write the energy balance for the system. So we can say, we go back to the main equation, dE by dt, which is the transient variation of energy within our system, equals to, so we can always start from the general equation, then start to simplify terms. So it's E dot generation plus sum of E dot n minus summation of E dot out. Here we want to see if there is a storage term. So we cannot cancel this. We are asking ourselves if it's zero or not. So we want to calculate it. Do we have any generation within the wall? Do we have any generation here within the wall? No.
Energy.
No. So this term will cancel out. What is the fluxes of energy coming in?
Conduction.
Yes, if you want, but it's equal to what? It is transferred by conduction.
Q double prime, yeah, basically.
Yeah,
exactly.
It's equal to the inlet flux because of the imposed heat flux on this face. Okay. Do we know the area here of the surface?
No.
No, but no need. We can just do the analysis per unit area. Okay, because we just care to answer the question if we have a transient term or a storage term or not. Okay, so here we can, if you want, because we don't have the area, we can find all energies per unit area. So E dot second, E dot in second, and E dot out second. So we have already sum of E dot n is plus 20 because we have a flux of 20 watt per meter square. And what about E dot out?
It's convection only, depending on the control
process?
volume.
Yes.
Convection.
Exactly, by convection.
Depending on your control volume.
Exactly, depending on the control volume. I consider the control volume the wall. Okay?
the wall.
Because
Yeah, then you
I
don't-
considered the whole wall. The wall is receiving a flux because I am imposing on it a heat flux, and it's losing a flux to the outer environment by a convection. Okay? Now, conduction is taking place within the wall. Okay, within the wall, inside. But when I take the boundary layer, just if you want, at the extremity of the wall, we can say that conduction will end just here. Okay, just at the adjacent. Yani, if you take particle of air adjacent to the wall, they will take heat by conduction. But whenever you want to transfer to the outer environment, it will be by convection. Okay, because only you have still air at the contact with the surface because of the non-slip condition that you know from fluids. And then because you have a fluid moving, it will transport this heat by convection. This is why we say that the wall will lose heat by convection process. And then E out is equal to, we just have to put minus because we are losing it. Because we are doing the analysis per unit area, we don't multiply by A. So it's just minus H times T surface minus T of air. T surface minus T of air. Okay, so we get, if we calculate the convection flux, it's 400 watt per meter square. So we are losing much more than we are gaining. So the net, if you want the net flux that is stored, which is a transient term, dE by dt, here it's a negative value. This means that we are losing. We are not storing energy. We are losing energy because the flux that is getting out is much larger than the flux that is getting in. And therefore, Q second net is minus 380 watt per meter square. So of course, what will happen with time, if we observe with time the temperature profile of the wall, will observe decrease in temperatures. Okay, because we have a net rate that is negative. Any question on this?
No, thank you, Professor.
Okay. Another problem. In electric resistance, we'll see in these problems that we can have different modes of heat transfer, and the energy can go from one form to the other, okay, depending on the given. So here, for example, here we have generation of energy because we have an electric resistance heater that is embedded in a long cylinder of diameter 30 millimeter. So we have a source of heat inside the system. In this case, okay, we'll have a generation term. When water with a temperature of 25 degrees and a velocity of 1 meter per second flows crosswise over the cylinder, the power per unit length required to maintain the surface at a uniform temperature of 90 degrees is 28 kilowatt per meter. Now, when air also at 25 degrees but with a velocity of 10 meters per second is flowing, the power per unit length required to maintain the same surface temperature is 400 watt per meter. Calculate and compare the convective coefficients for the flows of water and air. In this problem, we can understand, for example, how we do the design of cooling systems. Whenever you have, let's say, a cooling application, you should select a convenient fluid to perform the cooling operation. And of course, as we'll see here, the cooling effect of water is much larger than the cooling effect of air. And this is the case in general when you compare convection when using liquids. It's much important than convection when using gases because the liquids are characterized by relatively high values of H. Especially, even if you compare now what they did here, they increased a lot the velocity of air, which is giving advantage to air. But if you want to do comparison to be accurate, you should compare at same velocity. Okay, and you will see even here they increased a lot the velocity of air. You will still have much larger convective coefficient for water. We know that from convective heat transfer, H is depending on several factors. It will depend on the fluid. It will depend on the temperature. It will depend on the velocity of the fluid, etc. So you have several factors that can affect H, but the main parameters are fluid type and the velocity of the fluid. And from experiments, we have observed that in general H is much larger for same velocities. H is much larger for fluids than for liquids than for gases. Okay, here we try to increase a lot the velocity of air to see if it will have a cooling comparable to water that is flowing at relatively lower velocity. Even while decreasing the velocity by 10, water will still perform much better. That's why whenever you want to remove a lot of heat, you don't use gases, you use liquids. Okay, this is the case, for example, of the thermal combustion engine in your car. You use fluids as liquids to circulate in a cooling system in order to cool your engine. So here, let us do by calculations the comparison. Okay, let us see what we know. So as usual, we try to do a small scheme, including all given. So we have the electric resistor that is embedded in the system. We don't know its power. We know the power because they told us, look, they told us that when we are using water, the power needed to maintain a constant temperature is 28 kilowatt per meter. So this is the power per unit length that is delivered by the electric resistance. So we have a long cylinder, okay? We have a cylinder, and inside this cylinder, we have an electrical resistance, and we can pass by a current within the electrical resistance to produce a power. You know, in general, if you want to calculate the power, if they don't give it as a value, they can give you the resistance and the current. You know from electricity that the power is U times I, okay? Which is delta V, the voltage, times the intensity of the current. And since we know that for a thermal resistance, U is the resistance times I, then the power can be written as R times I squared. So in case they don't give you directly the value, they can give you the resistance and the intensity, and you can then calculate the power. Okay, so what is happening is in the first experiment, what we want to do, we have generation of heat by the electricity, but we don't want to increase a lot the temperature of the cylinder. We want to keep the outer temperature of the cylinder equal to 90 degrees. In order to not exceed this temperature because of heat generation from the electrical resistance, will pass a fluid over the cylinder for cooling purpose. Okay, and we started with water at a temperature of 25 degrees and the velocity of 1 meter per second. So we'll be able to cool by which type of heat transfer?
Convective.
Convection. Okay, so we have heat is lost from the cylinder by convection. So this is what we can say until now. Plus we have generation. So this is a source of heat. So we have heat generation here. Okay, now what we want to find, what we want to calculate is to calculate the convective coefficient in both cases. So let us start with the general equation. Do we have dE by dt here? If yes, why? And if no, why? Why we have dE by dt or we don't have it here? What is the condition to have a rate of change of energy with time?
We don't have the E by dt here.
We don't have. Why? Because look, we are
Very-
finding H in a way to maintain the same temperature at the surface. Whenever you
Exactly.
maintain a steady temperature that is not varying with time, so you have a steady problem. You are trying always to, if you want to provide cooling, okay, in a way to remove all heat generated by the cylinder. That's why you can keep steady conditions. So we don't have any storage because we are designing the problem, yani we are finding H based on the idea that we don't have any variation in temperature for the surface. The surface will be maintained at 90 degrees. This means that we are able to remove the heat generated due to the resistor through the convective process. So there is no storage term. Equals to, here we have E dot generation here, but because we don't have the length of the cylinder, then we will find all values per unit length. Okay, so all your values, if you want, you can put, we said that whenever we are calculating watt per meter square, uh we put E second. Here we'll put just E prime. Okay, so dE prime by dt is equal to E dot generation prime. This means that the unit is just watt per meter. E dot generation is the power generated per unit length of the electrical resistance, and it's given. They told us that in case of water, we need to supply 28 kilowatt per meter. So we can put that 0, which is dE by dt, is equal to E dot generation, which is here 28 times 10 to the power 3 watt per meter. So just please pay attention for units. So do not mix units. So if here you have other, if you are computing H in watt per meter square Kelvin, the E dot generation should be also in watt per meter. Okay. Now, do we have any flux of energy coming in? Do we have any flux of energy coming inside the cylinder?
Coming inside the cylinder, no, yeah, we have the
Look,
cooling, but
okay. It's cooling هو flux of energy getting out. But do we
no,
have any source giving heat to the cylinder to have En, E dot N? In general, we do plus E dot prime N
Mhm.
minus E dot prime out. Do we have any source of heat giving energy to the cylinder? غير الجنريشن. Generation is within the cylinder, but En means that from the surroundings we have a source of energy giving energy to the cylinder. We don't have.
No, we
No,
don't have.
we
Yeah,
only
sorry.
have a energy getting out to the environment, to the surrounding, and by this energy is getting out by convection. And because the unit is per unit length, okay, we can write it as follow. Who can tell me how we can write the convective transfer per unit length? What is the formula to use?
Per unit length,
Yes,
uh, H times the perimeter,
yes, very good. Okay. What's your
2 pi
name?
RL, not 2 pi R. Fadi, professor.
Okay, Fadi. So here, the convective transfer, heat transfer is written as HA times T surface minus T infinity, okay? But because we wanted per unit length, we should divide this by F. Now let us see together what is A? What is the area through which we have convection? It's the lateral area of the cylinder because the cylinder is exchanging through this area, through this lateral area, heat by convection. Okay, and to calculate this area, all we have to do is to consider the perimeter of the cylinder times its length. So we can replace A by pi d, pi times diameter times length. And because we want to compute it per unit length, L will simplify. And then we just have that the convective coefficient per unit length is pi times d times h times T surface minus T infinity. Here T surface is the temperature that we want to maintain. It's 90 degrees. We can keep temperatures in degrees here because it's not, it's linear, not like radiation. In radiation, it's T to the power 4. So please, in radiation, don't forget to convert to Kelvin. Okay? And T of air is 25. We have everything. We have the diameter also. The only unknown will be the convective coefficient H. So we can get from here what will be the convective coefficient due to water flow. Okay. Now, for air, the procedure is exactly the same, but you can just compare numbers. In case of water, okay, to keep a temperature of 90 degrees, you need a very the power used is really very large. However, when you have air to keep the same surface temperature, the electric power is just 400 watt per meter. So imagine the high cooling effect of water compared to air. So whenever we have water, okay, water can remove a much larger generation rate compared to the ones that can be removed from air. Even if we increase the velocity by 10 of air compared to water, the water will have a much better cooling performance. So that's why in general we recommend to use liquids whenever we want to have high cooling rates. So here, if you compare, the convective coefficient of water is of the order. Look, it's very good to know. You don't have to remember orders, but it's good for you to do verification and just know approximately the order. In the course material, we have given nearly the order of convective coefficient for different phases, if you have a liquid, if you have gas, etc. So you can see here that it's of the order of thousands, while for air it's less than 100. Okay, so and even the velocity of even with the high increase in velocity of air, we multiply the velocity of air by 10, the convective heat of water is nearly 70 times the one of air. So from here, the importance of appropriate selection of the fluid that you will use in your cooling application. Any question on this problem?
Doctor, are these problems posted on Moodle?
I will post them. Okay,
Okay.
I'll post them today. The problems on Moodle are different, but this is because I want to profit with you from time, because they are already solved and you have all recordings for them. You can do them as practice, and if you have any difficulty in the problem that I already posted on Moodle, and if you went over the recordings and you are finding any difficulty, we can tackle them during the live sessions. Okay.
Yes, thanks, Doctor.
Okay. Another application, a temperature controller for a clothes dryer consists of a bimetallic switch mounted on an electrical heater attached to a wall-mounted insulation pad. The switch is set to open at 70 degrees, which is the maximum dryer air temperature. To operate the dryer at a lower air temperature, sufficient power is supplied to the heater such that the switch reaches 70 degrees when the air temperature T is less than T set. If the convection heat transfer coefficient between the air and the exposed switch surface of 30 millimeters square is 25 watt per meter square Kelvin, how much heater power is required when the desired dryer air temperature is 50 degrees? So look, sometimes the description can seem complex, but in reality, when you want to see the energy equation involved, it can be a very simple equation. So here, for example, you have a system that is used in case of a machine to dry cloth, okay? But the concept is very simple. What you are doing here, you want to supply an electric power in a way to maintain this temperature, this surface temperature constant. So it's very, very similar if you want to the previous problem we have done now. Because you want to maintain a constant temperature of 70 degrees here, this means that you need to perform in steady operation. And in steady operation, you should make sure to, if you want, compensate for losses. And as air will move over your surface, it will take heat by convective effects. Okay, so to compensate for this loss, you should provide an electrical power to the system that consists of just passing a current through a resistance. Okay, so here mainly the energy balance is very simple. We have a steady state application where we don't have storage, um, and here we can consider generation, or en is the same. You know why? Because it depends how you take your system. What I mean by this, it's very important to identify your system. If you consider that, let's say for example, if I take a system and the resistance inside of my system, okay, so if the electrical circuit is inside of my system, then I can consider that heat is a generation source. However, let's say if you have the resistance passing like this, so the current is is entering inside your system, you can just consider it as an inlet energy. So it depends of the boundaries of your system. If your system is completely embedded in your control volume, you can consider it as a generation source. If the system is just crossing, let's say crossing your boundary, you can consider that this is a power, this is an energy that is coming in. So here you can write it as E dot N minus E dot out equal to 0. You can consider the electrical power as an input to your system, and the convective flux that is getting out from by air is E out, E dot out. And then you can just write the balance, which will tell you that the electrical power is equal to HA times delta T. And then you can compute what is the electrical power you should put in order to compensate for the losses you are getting outside of your system. Okay. Any question on this? Another
Professor.
problem. A spherical probe of 0.5 diameter contains electronics. So for example, here from the given, they told you it contains electronics. So you can consider that I have an internal source of generation that are dissipating 150 watt. So this represents automatically a generation term, E dot generation. If the probe surface has an emissivity of 0.8, so here, whenever they give you the emissivity, you can say that we cannot neglect transfer by radiation. In some problems, especially when you have forced convection over the surface, okay, convective transfer can be dominant over radiation. That's why they don't give you the emissivity. When they give you the emissivity, okay, and let's say they gave you, for example, a flow over the surface, you should consider both convection and radiation loss to the surrounding. Here, because they just gave emissivity, so you can consider that I have heat loss just by radiation mode. And the probe does not receive radiation from other surfaces, as for example from the sun. What is the surface temperature? And this sentence also is very important because in the course material we have learned how to calculate the net rate of radiation. We have seen that a surface can be surrounded by many other surfaces. And in case we have a big enclosure, we have demonstrated last time that we can compute a net radiation flux. where the net radiation flux will be equal to the emitted rate minus the absorbed rate by radiation. Okay, here because I told you we don't have any other surface that is exchanging by radiation with the sphere, so we just have the emission term only. We don't have to do minus the absorbed one. So now, if we do a small figure, we can take the control volume surrounding our probe, and then we just have the flux that is emitted by radiation. We have the flux that is generated by the probe, okay? And we want to solve for the surface temperature. Because here they asked for a surface temperature, this means that we are in steady case. We don't have variation of the temperature. We have steady case and we want to solve for the steady temperature at the surface. All we have to do then is to write the energy balance. There is no storage. There is no, if you want, inlet, okay, of energies. You don't have any input, just have an output and a generation of energy. So whenever you write the balance, the equation will be simply E dot generation minus E dot out equals to 0. Now, E dot generation is given, so just you have to express your E dot out, and since it's a flux of emitted radiation, then you can just replace it by epsilon times sigma. Can you tell me here what will be the area? What is the radiation area? What will be A here when we do the computation of A? What do we replace A by? What is the surface emitting the radiation?
The outer surface of the sphere.
Is the lateral area of the sphere. Exactly. And for a sphere, okay, the lateral area, A lateral, is 4 pi r square. Okay. So here when you want to compute, and you will see this again when you do the example of greenhouse gas emission that is involving radiation from the earth. Okay. So you will encounter again the surface of emission is 4 pi r square. Okay. So now when we replace all variables in the equation, the only unknown is the surface temperature, and you will get this, the temperature that you get will be in Kelvin. Okay, please pay attention for units. When you solve for TS, you will get TS in Kelvin. In case I want it in degree, you can do minus 273.50. Okay. Another problem. A long bus bar in cylindrical form for making electrical connection of diameter d is installed in a large conduit having a surface temperature of 30 degrees and in which the ambient air temperature is 30 degrees. So here I was telling you, pay attention for each sentence, okay? When they tell you that the long cylindrical rod is installed in a large conduit having surface temperature of 30 degrees, they gave you temperature of the enclosure if you want. So you can automatically think about radiation and about net radiation. You have emission and you have absorption. And also they gave you the air temperature, so you might have also convective heat transfer with air. Now, in addition, the electrical resistivity of the, if you want, inside your cylinder, you have a resistance. The electrical resistivity of the bar material is a function of temperature. Look, I don't consider that you should have electrical knowledge. So in case I want to give you something similar, I will, as in this problem, I will explain everything for you. You will see that in this problem, they will give you all formulas related to electricity. So you don't have to know them from before. So in any problem, I can give you, let's say, a new problem, new concepts, but all formulas needed will be given for you. So you can solve without any previous knowledge on this. And for example, it's not a problem if you don't know what is electrical resistivity. They will define it for you here. So the electrical resistivity of the bar material is a function of the temperature and is given by rho E 0 equal to rho E times 1 plus alpha times T minus T0, where rho E0 is given to equal to 0.0171, T0 is 25 degrees, and alpha is 0.00396 Kelvin minus 1. The bar experiences free convection in the ambient air, and the convection coefficient depends on the bar diameter as well as on the difference between the surface and ambient temperatures. And the governing relation of H is of the form of C times D to the power minus 0.25 times T minus T infinity to the power 0.25. As we discussed in general, the convective coefficient H depends on the situations that we have and will be function of the fluid. Here, because we are using air, we are using the same fluid, we are doing experiment on this, and we are trying to correlate H with geometry of the sphere, so with the diameter, and with the difference in temperature between the sphere and the surrounding. Where C is 1.21, and of course C will be depending on the fluid you use. Here we are just using air, that's why we got is this value for C. If you use another fluid, you'll get a different value. Now, the emissivity of the bar surface is 0.85. So here they gave you the emissivity. And as we have seen in the course material, now because you have the case of an object in a large enclosure, you can directly say that the net rate of radiation, so Q radiation net, okay, is equal to epsilon times lateral area of the cylinder times Boltzmann constant times T surface to the power 4 minus T air to the power 4. So you already you can see that you have all parameters. They gave you epsilon, you know sigma, okay? You have the value of T0 is given for us. Here, not T0, T infinity, we mean. The temperature of air, and the temperature of air is given, sorry, the temperature of the enclosure, okay? And the enclosure temperature is equal to air temperature. So we take here the temperature of the enclosure as T infinity, which is 30 degrees, and Ts is the surface temperature. So if you want to avoid confusion, I will put T surf T0 if you want, or also T0 is used here. You can put just T surface of enclosure, which is here if you want the conduit surface. So T conduit, we can call it. T conduit, which is also 30 degrees. Okay, so TC. This is the temperature we'll use here. So TC, which is 30, but don't forget to use it in Kelvin. Yani 30 plus 273.15